Welcome everyone. Thank you for joining us for today's webinar. I'm your host, Liwei Huang. Today is Earth Day. Happy Earth Day, everyone. At ABB, we embed sustainability in everything we do in order to create long-term value. I encourage you to visit abb.com or contact your local account managers for more information. Power slide 2, please. So before we begin, I would like to go through the webinar logistics. Today, we're presenting Optimized Process Safety Management through Digitalization by Carl Watson. Just a few housekeeping items before we get started so that you know how to participate in today's event. We have taken a screenshot of the attendee interface. You should see something that looks like this on your own computer desktop. The control panel hides automatically when not in use. You can bring it back by moving your cursor. You have the opportunity to submit text questions to today's presenter by typing your questions into the Q&A box of your attendee interface. You may send in your questions at any time during the presentation, which will last approximately 35 to 40 minutes. We will collect these questions and address them at the end of the presentation during the Q&A session. If you cannot locate the Q&A in your meeting controls, then click on the controls button with the 3 dots located on the lower right corner, then click on Q&A. This will add the Q&A box so that you can type in your questions. A reminder that all attendees are in mute mode, and today's presentation is being recorded and will be provided to you by tomorrow for your reference. Next slide, please. Please note that as our presenters are sharing information today, the slides you're about to see are subject to change. ABB does not assume responsibility for any errors or consequences of software or hardware described in today's presentation. So I'd like to go through a safety moment. As you know, the springtime comes and it's time to do some spring cleaning. Make sure that you replace the batteries in smoke detector or carbon monoxide detector. Make sure you're breathing clean air. You need to change your furnace or air conditioning unit filters, and then clean out the dryer vent. Check your medicine cabinet and the first aid kits. Make sure you're ready or available. You have the necessary resources available, and check for mold in your house. As we always say, health and safety is at the heart of what we do. Again, today's webinar topic is the optimized process safety management through digitalization. My name is Liwei Huang, a technical consultant for advanced services at ABB. I am based in Ohio. The presenter today is Carl Watson. Carl is the global sales leader for Safety Insight at ABB, and he has 33 years of industry experience, of which 15 plus years in safety as TUV functional safety engineer. He is based in Bellingham, Great Britain. Now, Carl, I'll turn it over to you.
Okay, great. Thanks, Liwei. Much appreciated, and thanks everyone for joining and sparing the time. I hope you find this next hour or so informative, and I look forward to the questions at the end. And I hope everyone is keeping safe. So I'm going to talk. I'm going to talk about some safety in the context of process and functional safety, and to make it real, I'll show some software that that can be used to help take a digital approach to optimizing your process safety performance. So the agenda here, we'll look at just a couple of slides on ABB's approach to process safety, just to make sure that everyone has a baseline of what we're talking about here. I will give a 5-minute whirlwind quick recap of the first couple of phases of the safety life cycle, just to make sure that everyone is level set. I'll then focus on some of the operational and maintenance clauses of the standard, and things that operators such as yourselves are required to do in the operations and maintenance phase, referring to the latest release of the current standard, and show you some of the changes there. And then, as I said, just a slide or two on the portfolio, which is Safety Insight, which can help you meet your obligations with regards to process and functional safety. And to make that real, I'll give you a software demonstration. So before we start, I always like to know who I'm talking to. So just going to be a poll question pop up for you guys. If you can just let me know what's your experience in terms of process functional safety. You've got 5 options here. No experience. I've heard people mentioning SIL and SIFs, but don't really know what they mean. I've got a base knowledge, but and I think I could explain it to someone. I've got detailed knowledge across the safety life cycle, or I'm an expert. So if you could just pick one of those options and let me know the experience of who I'm talking to. And the results should pop up on the screen at the moment. So the time elapsed is completed. Just waiting for the results to come through. Okay. All right, good. So middle ground, that's good. What I will then do is, forgive me those that are in D&E. Forgive me, I'll take a relatively quick view of this, so I appreciate what I'm going to talk about in the next few slides is more detailed and complex than that. Please don't pull me up. I'm just making sure that everyone's got a level set. So the B's and C's, just want to make sure that everyone here has got a common understanding of what I'm talking about, and then we can make it relevant in the software. So great, thanks very much for your responses there. So I mentioned about ABB's approach to process safety, and this through the services they provide, but also through the software that we also provide as well. We're taking the 3 questions that were posed post an incident a few years now, back in 2005 at the Buncefield Storage Depot in the UK. So the Health and Safety Executive, which is the regulator here in the UK, posed high hazard industry should be able to these 3 questions, which we should be able to answer. And those 3 questions are: we need to understand what can go wrong. That's question 1. We need to understand what systems and barriers are there to protect against it. And then we need to have information to assure those barriers and systems are working. So 3 very simple questions that I think, if as an industry, if we can answer those 3 questions robustly, we'll be in a much better place. So the way that we approach this as an industry, we do risk assessments, things like HAZOP studies and LOPA studies. That helps us understand what can go wrong and what's there to protect against it. For the different barriers and protective systems and independent protection layers that we identify, then we design it. So we design an alarm system, we design a safety system, we design a relief stream system, all the different protective systems we design. We implement it, and then we move into the operations and maintenance phase, where we need to sustain a level of safety and look for improvements. So the improvements implies that we're in a life cycle, and the life, it is a safety life cycle. So here we've got the 3 questions and those 4 phases wrapped around it. So adopting this life cycle approach allows us to bring digital. So in digital, we're going to connect more and more systems together to produce more and more data. So that digitalized operational data is often termed IT/OT. So that's information technology and operational technology. Operational technology from your automation system, information technology from your maintenance management system. So we're going to produce more and more data, but we need to turn it into actionable information. And to do that, what we need is the engineering data in a format to be able to give context to the data and turn it into information. And that's termed ET, engineering technology. And the idea is to be able to link the 2 together and get actual operating experience and feed it forward to validate the design assumptions made in the early life cycle. So that's our approach, and that's how to answer those 3 questions, and also how we bring digital into the story. And in my software demonstration, I'll give you a couple of simple use cases of how you can apply that. So as I said at the start, I'll give a recap, a very simple, basic recap of the standards here. And as I say, don't pull me up. This is, I know it's more detailed than this, but this hopefully will give everyone a level set. So this is the functional safety standard according to 61511. And we can effectively break it up into those 4 phases. So if we look at risk assessment phase, first of all, I'm just going to give you a very simple example to take people through so we get a common understanding. So if we just look at this vessel here, we've got a vessel with hydrocarbons come in. Just use my pointer here. Hydrocarbons coming in. We've got a level controller controlling the level in here. So risk assessment. What could go wrong? Well, we have a level controller failure. The level could rise in here. We could have overfill. We've got a release of hydrocarbons. If that finds a source of ignition, then we're going to have a fire or an explosion. And that's going to have some safety, environmental, and business impacts. So obviously we don't want that to happen. So we then start to put protective systems in. So that answers the question on what can go wrong. So protective systems. So we could put an interlock on that level controller. So when the level goes up a little bit, we open the valve to stop it overfilling. That could be one protective system. We could put an alarm in place. So once the level gets a little bit higher, then we alarm to the control room. Control room takes independent action, and the level comes back down again. And then ultimately, we put in the safety system. And this is functional safety, because upon some function, which is high level in this case, we perform some action, which is in this case, stop the feed flowing into the vessel. So we get extra high level, we stop the feed going in, and the hazardous event is avoided. So that's a simple exercise of a risk assessment. But then from a risk perspective, is that safe? And do we really need that safety system? Or do you think that the alarm and the interlock is sufficient? And we can't do it by inspection. We've got to do that risk assessment. So very briefly, just going to explain what that means. So all these standards, these functional safety standards, are risk-based. What do you mean by that is that the risk of overfill is, we're not saying that it will never happen. We're saying that the risk is of that overfill situation leading to whatever consequences is acceptable to our business. So we start with the inherent risk from the process. So that's the the likelihood of the level control failure or a person making a mistake leading to overfill. We've then got what is acceptable, and that's set by the operating company. And the idea of this risk assessment is reduce the risk from the process risk down to the target risk level. And we fill that risk reduction with things like the interlock and the alarm. That takes us so far towards where we want to get to. If there's a gap in this instance, well, we need some more risk reduction. If that takes us where we need to, we start to answer that question that if we need the SIF or not. So in this instance, we do need additional risk reduction, and that's what we provide by the SIF. Those two together give the actual risk reduction, and there's some inherent risk still there. And the size of that box at the end is equivalent to the safety integrity level. So now, based on that risk assessment, we can say yes, we do need that SIF. And once we apply a SIF with a specific safety integrity level, will be considered as acceptable in terms of the risk levels. But we don't talk about size of boxes in terms of safety systems. We talk about SIL levels. So what's a SIL level? So if we've got a SIL of less than 1, that's a risk reduction of 10 or less. That actually falls outside of the requirements of the standards. If we've got a risk between 10 and 100, that's SIL, risk reduction of 10 and 100, that's SIL 1, and then orders of magnitude up over. But also when we're doing the calculations, we need to look at something called the probability of failure in demand, which is the inverse of the risk reduction. So for less than SIL 1, it's 0.1 or small or larger, sorry, and then 0.1 to 0.01. Quick way of checking this PFD number against the SIL level, just counts the zeros after the decimal place. That tells you the corresponding SIL level. So that's the first step. Do your assessment, determine if you need a safety system in place or a safety function, and what safety and level do we need, and what probability of failure demand or risk reduction, depends how you do how you quantify it. So that's the first step. Then we'll look into the design step. Again, recognize this is more complicated than this, but for the specific, a lot of the requirements in operations and maintenance, this is the key to it. We look at what is that system that we're going to reduce the risk with. And in this instance, it's a level transmitter going through a safety system, going to operate, that safety system is going to operate a solenoid valve, which is then go, in this instance, close the trip valve, which will stop the feed going into the vessel. So that's the system. All of these components can fail. I need to look at something called a dangerous failure rate. What's a dangerous failure rate? So this valve here, normally open to allow the flow to come through. If it sticks open, we don't know it's stuck open until we need it to close, and that's called a dangerous failure. So what we do is we have assigned a failure rate for each of those components. Here's an example of some failure rates. So level transmitter failing about once in 15 years, solenoid valve once every 30 years, valve once every 30 years. What we do in this phase of the design, we calculate the sum of the dangerous failure rates, pop it into the PFD average equation, and we use this equation to work out how often we want to test it. So the idea here, proof testing is the thing that we need to work out how often we need to proof test it. And the reason we proof test it is to find those dangerous failures. So that valve there is normally, if it normally open, if it's stuck open, there's only two ways that we can find out outside of diagnostics if that valve is stuck open. One, through the high level situation, which leads to the event. Obviously, we don't want that. So therefore, the other way is to test it. So we simulate a high level and we check that the valve closes, and when it doesn't, find out there's a fault, and therefore we fix it before the demand occur. So we got to do this testing, and the idea of this calculation is to work out how often we test it. So let's assume I'm going to test it every year. Pop that in the equation, we get this number here. It's a SIL1 number, and let's say the target was SIL1, then this should be okay. However, there's a band. So if the target's 0.025, a risk reduction about 40, based on that design, we haven't got a big enough box to get to the target line. So therefore, we've got to adjust it. So we either change the architecture or we change the frequency that we test it. So let's assume I'm going to test it every 4 months, pop that into the PFD average equation. That gives us a lower PFD average, a higher risk reduction. It makes the box a little bit bigger than it needs to be, and everything's good. So that's a very quick summary of the first two phases of the life cycle. And I just wanted to do that just to give everyone a level set to make sure that the rest of the presentation makes sense. Okay, so what do we next? We then, as I pointed out earlier, we then do the implementation, and we do the commissioning, and we do the validation. So the actual implementation is meeting the requirements that we've defined in the risk assessment phase. And then we move into the operations and maintenance phase, where we need to continue to make sure that we're meeting that risk reduction and validate it by closing the loop. And I'll talk a little bit more about that in a moment or two. Okay, time for a second question here, which is about proof testing. So I've talked about what a proof testing is, where we prove the safety system. It's there to identify those dangerous undetected failures. So if you could just let me know when you do the proof testing and what's the impact of it on your operations. If you could just pick out one of the answers that's closest to where you sit for your operations. Okay, quick whirlwind there, so your time's up if you weren't quick enough on it, but hopefully some results will pop up. Okay, so all right, so for those that are done D, great, you're in a nice position. I guess you're a lot of sort of batch processes in there in that processes, but where we've got continuous processes, you therefore, obviously, like was just saying, closing that valve will have some impact in production. So therefore, if we then do it outside of turnarounds, that's going to have that impact in production. If you then only do it in a turnaround, so you have the impact in production, what you then tend to find is that this is the last thing, these testing is the last thing that gets done in a turnaround, because you've had to put have to wait till all the other maintenance done, put the plant back together again, and then test the safety system. So it's the critical path. So that's good insight into that. So thanks for your responding to that. Okay, just want to talk some of the insights into this session was about, you know, how do you demonstrate compliance? So some of the objectives of this session was how do you demonstrate compliance? I'm not going to go too much detail on it here, but hopefully you can see I've picked out a few of the clauses associated with the standard that shows what I've just talked about is quite key. But also it's not just about compliance. There's opportunities here for everyone if we take the right approach. So the items that I'm showing here in red are arrived in addition to the standards, the 61511 standard at the end of 2016. So about 4 years ago now. That they've been in place. So the first thing to say is that reliability data needs to be credible, traceable, documented, and justified based on field feedback, based on similar operating conditions. So saying we can't just grab a number off a data sheet and take that and throw into the calculations. We've got to make sure that really the data that we populate is based on field in similar operating conditions. So that's a point to notice on that. The black text is what's been in there since the start. So back in 2003. So in 2003, it's always said that some periodic intervals, the frequency of testing shall be reevaluated based on various factors, including historical test data and your experience. So one is saying that there's other clauses say that you should be testing. Well, actually not should, shall be testing. But this is saying you should be doing that feedback. You should be gathering data and closing the loop. And what I've got from a lot of our customers is say, yeah, recognize that, but it's been too difficult. So hopefully I can show you some ways that we can quickly help you with that. New note. Okay, it started a little bit at the start of the character, so you can adjust that frequency based on data. It said you should have, it's always said you should have procedures to collect, to plan and collect the data. Now we're saying we should collect data on demands and reliability. So a new clause in there specifically linked to that top clause. But here's the carrot. So it's not just about compliance. We've now got a note in the standard that says if you collect data to demonstrate that your reliability of your equipment is better than your first thought, you can then reduce maintenance. So if we're reducing the maintenance, introducing the frequencies that you are performing proof tests, then those that were in B and C either impact outside of turnarounds, then that by reducing maintenance will have reduced impact on production. And for those that do it in terms of the turnarounds, if we can extend it out, extend it longer, then your turnaround intervals can also extend as well. So therefore your intervals between turnarounds extend, means you can improve increasing your production in between turnaround periods, and shorten your turnaround if is another angle as well. So there's the requirements for you to do here, but also there's the opportunity for us to go forward if we collect the data and analyze that data. A couple of other points here. For me, criminal, the addition one of the standards didn't really cover bypasses or overrides of safety systems. Now there's a lot in the standards. Here's just a few of the items saying that we should have a bypass log, and we should look at these. Should be informed, provide information about what they should be doing before a bypass is put in place, then the maximum time to put that bypass in place, and then also things we should do an assessment to be able to ensure that we've got compensating measures in place. So when we take the safety system out by a bypass or override, what we're going to put back in its place to make sure that we stay where we should be in the acceptable risk. So that's another point that's come from the standards. And a final one, which is on demand tracking, just emphasizing a point I said earlier, that we should be tracking. It's just emphasizing the need to close that loop. discrepancies between expected behavior and actual behavior. Shall be analyzed, so it's not should, it's shall. Lots of shalls in the operations and maintenance clauses, which means the mandatory requirements. But now they've specifically said we should be looking at the demand rate, not just the failure rates as well. Okay, so that's a little bit about the clauses. Things that you remember, the black there have been in since 2003. The red lines are new additions that came in 2016, so 4 years ago. So these things should start to be put in place. All right. So now what I'm going to do is just start to just recap. So that need there of closing the loop and gathering IT, OT data and validating, closing the loop and validating the base assumptions which you've got in the engineering technologies. That's the need, and to support that need, we've got a suite within ABB. We've got a suite of applications, engineering applications to digitalize the basis of safety, or digitalize that that engineering data, create something called a process safety digital twin. This is how you are safe in this phase, and we've got HAZOP, LOPA, and SIF designer modules to assist with that. And then in the operations and maintenance phase, that's gathering the IT, OT data to make sure that the safety systems remain effective, you manage operational risks, but also you close that loop and look for areas for improvements. So rather than talk about this much more, I think it's more powerful if I show it in software. But before I do, I just want to get a feel again about how you are with closing the loop. So gathering actual operations and maintenance data and feeding it forward to validate the assumptions in the that we made in the engineering phase. So last poll question before I go into the software demo, if you can pick up which one of these answers seems the most applicable. Okay, so what I'm looking here is how do you close that loop, revalidate the risk assessments of the design phases? Do you do it? You don't do it every 5 years. You gather it every 5 years, but we adjust it necessary, or we collect it routinely and update it. Okay, so there's a couple of collecting the data on a more frequent, on that 5-yearly interval, and if 1 or 2 doing it a little bit more often than that. Okay, perfect. So hopefully all got a level set now of what this is about, understanding the needs based on the standards. Now I'm going to hopefully try and make it real in the software. So what I'm going to do first of all is just that point I said quite at the top there about digitalizing your engineering data. So all that HAZOP and LOPA data that you've got in Excel spreadsheets and proprietary databases tucked away that no one ever looks at. That is your basis of safety. So if we take that, digitalize it, put it onto your risk matrix, and remember the risk, everything is risk-based. So here's the high risk, the unacceptable risk. So this shouldn't be allowed. And this is where we should be operating over here. Each one of these numbers is a HAZ event on a facility, and we can filter across multiple facilities for those events. And it's where we designed the facility to be. So that example that I looked for, if I just want to check what the hazards associated with that vessel, I can now, rather than trying to find the Excel spreadsheet and proprietary databases for HAZOP and LOPA, I can quickly look at that vessel. What's the hazards associated with that vessel? And now we can start to see, well, I appreciate this may be a little bit small, but this is overfill of the vessel leading to release of hydrocarbon, ignition leading to pool fire and an explosion. That's the hazard that we assessed several years ago. It's digital. We can access it readily. What's the potential consequences of that? Well, there may be typically 1 person present there, so we can then say that the hazard has a potential to kill 1 person. That's from a safety perspective. We can also look at it from an asset and production losses, and also we can look at those hazards from an environmental. So different consequences to those. And if we want to, we could pull up the LOPA assessment here, or we can look into more friendly view in this operational risk dashboard view, where we look at the links between the hazards, the causes, the different protective says. Remember, we had an interlock, we had an alarm, we had a SIF, and now we've got some mitigation barriers such as occupancy and ignition probabilities. And here's the consequences. So potential fatality, potential for release into drains, that's a lower severity event, or we've got potential production losses up for a month due to this consequence. So that's how we can digitalize that data and then start to use it for decision support. That's your ET, engineering technology data. Now feed this with operations technology data from the automation system, and also feed it from your maintenance management system. So what I have here is just a test tool. So we would capture this data automatically. So we don't expecting people to be manually entering this data into the system. So capture it through connectivity to your automation system or your maintenance management system. And when an operator, let's say an operator has a problem with a level controller, puts that level controller into manual, that generates an alarm or an event, maybe. In this instance, it would be an event. We can capture that event in our bypass list. So the bypass don't have override lists don't have to be specific to SIFs. They can be against any protective system. So immediately we capture that, but also we start to capture what's the view on risk. So now we can see here that when we designed the system, we designed it to be in that cell C3, which was medium levels of risk. But now, because an operator had a problem with a level controller, they've taken that into manual. That interlock will no longer work because it's in manual mode. And what we can now see that from our protective system, this interlock does not work, and we've got less systems in place. And the effect of that is that we've got an increased risk. So I'm just going to quickly accelerate this. So that's on manual. That person goes off shift. Another shift person comes on. The level rises, starts to hit the alarm threshold, causes a nuisance alarm. So then another operator on the next shift doesn't know the controllers in manual, sees that nuisance alarms, shelves that alarm, doesn't ask any questions. As soon as you do that, that status automatically captured in our bypass list, and now we can see the impact on risk. So 2 different actions by 2 different people at 2 different points of time, we can now see that the risk level is moving towards very high for this specific event. If we then extend it a little bit further, a maintenance person now is being told, hey, I've got to do one of those proof tests on the safety system. They come along, we're operating at this point in time, come along and then put the maintenance bypass in place on the safety system. Just to recap, all of these events are captured automatically in our system. We then got the list of degraded barriers. Now, if these were the only degraded barriers, only 3 degraded barriers across all your facilities, you probably said, hey, aren't we doing a good job? But actually, because those 3 systems are linked to the same hazard, the actual operating risks are very high. So here we can see we're operating at 3 orders of magnitude higher risks. Why? Because the controller's in manual, because there was a control problem, the alarm, that caused a nuisance alarm, so we masked the alarm, and then the maintenance person is doing some maintenance on the safety system and has had to bypass it. So now we're down to chance, whether a person is there or if the person makes a mistake. Okay, so that hopefully makes sort of a good example of that opening statement about getting your engineering technology data, your basis of safety, digitalizing them. That tells you what can go wrong, what's there to protect against it. Then we add IT, OT data from your automation system and your maintenance management system to then answer the third question. Do I have information to show those systems are working? Yes, I have. None of them are. And the impact of risk, the cumulative impact on risk is very high. So therefore, we can then take the immediate actions to reinstate those barriers and return the risk back down to acceptable levels. So that's the IT, OT, ET discussion. So what I just want to do is very briefly for the last few minutes of this demo is then start to look about how we can optimize the cost of safety. I talked about the requirements to do this proof testing. So let's have a look about how we can also capture OT data to facilitate that. So let's say that your facility is running and you have an unplanned shutdown. So you get high level in a vessel, facility shuts down, all eyes then turn to the maintenance engineer, or sorry, probably the safety engineer, to say, hey, answer these questions. What happened? Did the safety system work correctly? And can I start back up again? So 3 important questions. So the person then, the safety engineers typically has to go into alarms and event logs and start to decipher what happened. So on complex facilities, that can take a lot of time, all of which you're losing production. So let me just going to take you into the automatic shutdown report. So what we do here is we take a digital twin of the safety system. So using the cause and effect diagrams. So we know what should happen. We map that with the events. And then when we have an automatic, once we have a shutdown, an unplanned shutdown, we generate this automatic shutdown report. What does that do? Answers the 3 questions. What happened? We had high level in the production separator. Did the safety system work correctly? That's question number 2. Let me look at everything. As default, we just show what didn't work. So, but here we can see in this instance, yep, all of these valves closed in the right time. However, one of the valves didn't close in the permitted period. So there was a travel time fault on that particular valve. It did close, but not in the permitted period. So now we can use this data to immediately initiate that corrective action to fix that travel time fault and then start the facility up. If in the instance that everything worked correctly, the safety person can then use this report to say, yes, high level in the production separated safety system worked correctly, start back up again. And that's how we can use this data to help your operations. So that's one of the modules. We can use that data. Another one is, well, we've just, remember that what the need there is to perform proof tests. We've just had an unplanned outage, which has performed in anger a test on those valves. So the majority of the valves have just been tested. So why, if SAP or Maximo, whatever your flavor of maintenance management system comes along with a work order next week and say you need to do your yearly test, why? You've just proved that the majority of the valves worked correctly. So reuse that as independent evidence to reschedule that maintenance work. Obviously, the valve that had a travel time fault would have to wait until we've retested it, prove that it's working, and then that also gets reset to the interval as well. So that's how we can use the data to optimize that proof test activities. We can also start to use it here to look at do some investigative work on the valve. So if we look at the valve that failed, we can go back in time here and then just do an update on there. So we can then start to look at all the different actions of that valve. And this was the error that occurred over here. So we've got some pre-alerts. If I look in this valve operation summary, here you can see what we're doing to create that travel time plot is collecting all of the times that valve moves, whether it's part of operations or whether it's part of safety systems. We had some pre-alerts here. Those pre-alerts weren't acted upon, and now we've got an unplanned shutdown that we need to do some hastily emergency maintenance. If we don't have the spare parts to it, then that can lead to a prolonged outage. So that's a module that can help you optimize that proof testing activity. Final module before I close and move over to Q&A is where we start to collect the actual performance data. So here, what we can see is a list of the SIFs. You'd have more SIFs in your system than what we've got here. But what we can see here is the design PFD average that was calculated, and we're collecting data now to be able to work out what's the updated PFD based on your data. So the way that we get that, we can actually use this as a repository for people to manually record it, or we can connect to the maintenance management system and pull that data across into here. So if we look on here, just to prove that I'm independent here, I've got some Rosemount 3051 transmitters in here. in this system, this demo system, we've got a load of instances. This is the number of hours of operations. This is the number of tests, number of failures, etc., that we can collect. We roll all of that up to work out what the actual failure rate is, and then we then compare that against the design, and that's what goes into the updated PFD average equation. So that's collecting actual performance data, closing the loop, and then you can start to see a gap here. So we're proving that the instruments are better than we thought, and therefore for the same target, we can begin to extend the proof test intervals, exactly what that note said in the standards. One final point is about, obviously we've got the event that we looked at, and what we can then also do is in here, look at the event. We can then start to say, evaluate what happened here. Well, it was an actual high level. We can look at the causes here. So it was a level control failure. That was the cause of it. And then we can capture that. And then if we come back into the SIFT data, now we've got one actual demand here, which is then allows us to create the actual demand rate data and compare that against the design assumptions. So this is key here because we work on the probability of failure in mind. So the more systems get demanded, the sooner it will fail. So that's from a safety angle, but also when things are getting asked to operate more often, when we have that will lead to an unplanned shutdown. So therefore, that's costing us money. So we can use this data to say, hey, we're having more demands on the safety system. As I've just entered, why? Because we're having, what's the cause of that? Failure of the control system. Well, why is the control system failing? Because it's always in manual. Well, why is it always in manual? Because it's poorly tuned. So we're starting to do that root cause analysis and identify the causes of these failures. So there's a great improvement. Tune it correctly, educate the operations team to keep it in automatic mode. Keeping it in automatic mode produces less demands on your safety system, less demands on your safety systems, improves your safety, but also improves your uptime. And that's a great example of closing the loop so you can optimize the cost of process safety. So I'll pause there and hopefully open it up to some Q&As.
Yeah, thank you, Carl. So just as a reminder to the audience that you can type in